Good day. Let us focus on international standards, laws, theory, principle, and prediction. Start concentrating on standard units. Consider the case of aircraft fuel miscalculation. First, remember the signs. Aircraft fuel may be stored in liters, but aviation calculates fuel in kilograms. Why? Because aircraft safety depends on weight, not just volume. Aircraft safety depends on weight, not just volume. The passenger aircraft needed 22,300 kg of fuel, but during calculation, a mix-up in units happened. As a result, the aircraft became 15,000 liters short of fuel. Mid-flight, the plane actually ran out of fuel. Life-damaging error. A small unit mistake created a huge danger. Not engine failure, not bad weather, just confusion between kilograms and liters. That's why science uses standard units like the International System of Units to avoid confusion and errors. So a unit mix-up almost crashed an airplane. Of course, the pilot saved the people. The aircraft needed 22,300 kg of fuel. Some aircraft systems and countries then used kilograms, others used pounds. Further, fuel tanks stored fuel in liters. Remember, 1 liter of fuel is 0.8 kg. 1 liter of fuel is 1.77 pound. Both are correct, but only if the units are used properly. The crew should have used 1 liter is 0.8 kg and calculated the required fuel as 22,300 kg divided by 0.8 kg, that is 27,875 liters. But instead they used 1 liter is 1.77 without noticing it was in pounds, not kilograms. Reason being, at the time different countries and aircraft system still used different units like pounds and kilograms, which led to the confusion. So the calculation was 22,300 kg divided by 1.77 pounds, approximately 12,600 liters. Using 1 liter is equal to 0.8 kg, we had earlier calculated 27,875 liters. Minus it with 12,600 liters we calculated now. We arrive at the shocking result of 15,000 liters short. The pilots had the shock of mid-flight fuel crisis. Luckily, the pilots managed an emergency landing. This happened because units were mixed up. A tiny unit mistake created a huge real-life danger. That's why science depends on standard systems like the International System of Units to avoid confusion and errors. That's why aviation uses kilogram for fuel calculation and aircraft fuel is measured in kilogram because weight matters more than volume. Our vegetable vendor also use kilogram as standard units. Science helps us understand the world in different ways. A law describes a pattern in nature. It tells us what happens. A theory explains the reason behind it, why it happens. A principle is a general rule that helps us apply scientific ideas, and a prediction tells us what is likely to happen next based on evidence and understanding. Together, laws, theories, principle, and prediction form the foundation of science. A scientific law describes a pattern observed in nature. For example, Newton's law of motion explains why we feel a jerk when a bus stops suddenly. Laws tells us what happens, often using clear statements or mathematical relationships. A theory goes a step beyond a law. While laws describe what happens, theories explain why it happens. For example, atomic theory explains how atoms combine to form molecules. A theory is not a guess, as evidence is the premise. A principle, on the other hand, is a broad idea that helps us understand situations around us. For instance, the law of conservation of energy helps explain what happens to our energy while climbing stairs. We are tired sometimes, right? That is, energy is transformed, not lost. One of the greatest strengths of science is its ability to make predictions. Using laws, theories, and models, scientists can predict what may happen even before an experiment is performed. Using ideas of motion, we can predict how far a football may travel. Using chemistry, we can estimate how much carbon dioxide is produced in a reaction. Using biology, we can predict how breathing changes while running. These are not random guesses. They are recent predictions based on evidence and careful thinking. When predictions match observations, confidence in science grows stronger, and when they do not, scientists re examine their ideas, measurements, and assumptions. This is the true strength of science. It learns, improves, and corrects itself based on evidence. Prediction also estimate how soft bread will be after baking. Imagine Varsha saying it will rain today because the clouds look dark. A scientific mind like Meghna asks deeper questions. What is the humidity today? Is the temperature dropping? What was the weather like before previous rains? She looks for measurable evidence and patterns. Science remains open to correction by nature itself. Have you ever wondered why a weather forecast says rain today, but the sky stays perfectly clear? Weather is actually very complex. It depends on many changing factors like temperature, air pressure, humidity, and wind. Scientists collect measurements from satellites, radars, and weather stations and use powerful computer models to predict what may happen next. But here's the challenge, even a tiny change in one condition can grow over time and completely change the result. A small shift in wind direction or temperature today could lead to very different weather tomorrow. That's why weather forecasts are usually quite reliable for a few hours or a few days, but becomes less certain further into the future. This doesn't mean science has failed. In fact, it shows how science works with evidence, constantly improving its models and predictions to better understand nature. You may have heard the claim food should not be eaten during an eclipse because it becomes harmful. But science encourages us to ask simple questions before accepting any claim. What exactly happens during an eclipse? An eclipse is simply a play of shadows caused when one celestial body blocks the light from another. Does the temperature suddenly change drastically? Does food spoil just because it is kept in a shadow? Is there any physical, chemical, or biological change happening to the food? When we examine these questions scientifically, we find no evidence that food becomes harmful during an eclipse. This is how science works. It does not depend on fear, opinion, or tradition alone. It asks questions, looks for evidence, and searches for logical explanation. Scientific thinking helps us separate beliefs from evidence and understand the natural world more clearly. First, understand the situation being studied, then identify the quantities that matter, and finally make a rough estimate to check whether an answer makes sense. Exact values are not always necessary, especially in the early stages of reasoning. Approximation is accepted. Science is not about memorizing facts, it is about exploring. Imagine a family of four sitting down for dinner every day. Rice is served at every meal, steaming on plates, filling bowls, and slowly disappearing from the kitchen container. Now ask a simple but powerful scientific question. How much rice would this family need for an entire month? At first, the answer may seem impossible to guess, but science often begins not with exact numbers but with reasonable estimates and an assumption all calories came from rice alone is set. An average adult needs about 2000 to 2500 kilocalories of energy each day. Now let us take an average adult needs about 2000 kilocalories of energy every day. Now 100 grams of rice provides roughly 350 kilocalories. So to get 2000 kilocalories, one person would need about 600 grams of rice per day. Now imagine a family of four. 600 gram into 4 members is 2400 grams. That is about 2.4 kilograms of rice every day. For an entire month, 2.4 kilograms into 30 day approximately 72 kg. So a family of four would need roughly 72 kilograms of rice for a month if all their energy came only from rice. This is the power of estimation, not exact, but sensible enough to understand the real world. Are you ready for an activity? How much do you breathe in a day? Take a slow breath in, then another. Without even noticing, your body repeats this process thousands of times every single day. But have you ever wondered how much air do we actually breathe in one day? Is it 100 liters, 1000 liters, or more? At first, the number sounds impossible to estimate, yet science often works by making simple observations and building rough approximation from everyday experience. A resting person breathes about 12 to 15 times every minute. A day has 60 into 24 equal to 1440 minutes. The total number of breaths in a day is roughly 15 into 1440, approximately 20,000 breaths. Now we need to estimate the amount of air in a single breath. Instead of using complicated laboratory instruments, imagine blowing up a rubber party balloon. A typical balloon holds about 2 liters of air and it may take around 4 to 5 breaths to fill it. That means one breath contains roughly 2 liters divided by 4 breaths, approximately zero point 0.5 liters. So if each breath is about half a liter, then the total air breathed in per day becomes 20,000 into zero point 0.5 is equal to 10,000 liters. That is about 10,000 liters of air every day. The number sounds enormous. So how can we check whether it is reasonable? Let us return to the balloon example. Suppose you can inflate one balloon in about 20 seconds. That means you should fill roughly 3 balloons in a minute. Since each balloon holds about 2 liters, 3 into 2 is 6 liters per minute. Over an entire day, 6 into 1440 minutes is equal to 8640 liters. This is reasonably close to our earlier estimate of 10,000 liters. The two methods do not give exactly the same answer, but they are close enough to increase our confidence that the estimate makes sense. This is how scientific estimation works. The goal is not perfect accuracy, but a sensible answer based on observation, logic, and everyday experience. Blowing balloons all day would exhaust you, but normal breathing is effortless. During the COVID-19 pandemic, masks became part of everyday life. We wore them in classrooms, buses, hospitals, and markets. But a simple question hides behind this familiar object. How does a mask actually stop something as tiny as a virus? At first, it may seem impossible. Viruses are extremely small, far smaller than the visible holes in a cloth mask. If the gaps are larger than the virus, why does the mask work at all? The answer reveals something important about science. Real world problems are rarely solved by one subject alone. Biology tells us that viruses usually do not travel alone. When a person talks, coughs, sneezes, or even breathes, tiny droplets of moisture leave the mouth and nose. These droplets spread virus. Physics helps explain what happens next. Air does not move through a mask in perfectly straight line. Instead, it twists and flows around a maze of fibers. Larger droplets crash into fibers and get trapped. Chemistry explains why masks are made from special materials such as polymer fibers. These fibers are lightweight, flexible, and can be arranged into dense layers without making breathing impossible. Mathematics enters quietly in the background. Scientists use mathematical models to calculate airflow, estimate filtration efficiency, and predict how well masks reduce the spread of disease in a population. So, a mask is far more than a piece of cloth. Scientific thinking will be very important in whatever you do. It helps you understand the technology that surrounds you and helps you evaluate information critically and make sense of the world you live in. If you love this video, subscribe, keep practicing. Remember, science learns, improves, and corrects itself based on evidence.